Junior Cycle Higher Level 2014 Phase 3 paper 2, question 3. This is a statistics question, and it starts off by giving you some data, two sets of data, which we're going to probably be asked to compare against each other. And the first thing it asks is for a back-to-back stem-and-leaf plot. Well, when you do a stem-and-leaf plot, it's appropriate that you make sure that within each branch the leaves are in order. So there's a space at the beginning here which you can use to do a little bit of work on the data before you then actually enter the data in an appropriate order. So this stage I seem reasonably organised with the first one, and so what I should be able to do is enter that data in. So we have 79, we have 86, 89, 94, 96, 96, 97, 103, 104, 104, 105, 108, and then we have 111, 115 and 119. And I checked my data. I've done everything. I've done all the values. There's 15 values there, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I'm happy that data's in order. And you'll notice for my left-hand side stem-leaf diagram, I'm working right to left, working out from the centre. So I now move on to the second set of data. And once I've sorted through the data, I can now enter that onto the stem-leaf diagram. So 83, 94, 97, 97, 99, 102, 105, 106, 108, 108, 111, 11, 14, 17, and then 120. Then the last thing I need to do is do a key. And the idea is to explain exactly what we have. It's an opportunity to put in your units of measurement as well. So if I just put in the number 9 in there, let's say for sake of argument, 94 there or 94 there, okay, and you would say it just means 94. And very quickly, I forgot to do a double check. There's 15 values there, and there's 5, 10, 15. There's 15 values there, so I'm fairly certain I've mapped the data on in a correct manner. And it's now a matter of using that data and finding some values to represent it in terms of averages and measures of central tendency and various other values. So the first thing it asks us is for a range. Well, a range is simply the idea of the maximum value subtract the minimum value. It's the difference between the highest and the lowest. So in this instance we have the difference between 119, which is the highest value, and 79, which is the lowest value. And the answer is 40. The max take away the min for the second set of data is 120, take away 83, which works out as 37. So from those values, what they tell us is that since the range for the second test is smaller, but only by a small amount, we can see that the test 2 is spread out into a lesser extent. Test 1 is more spread out. Moving on to the next question over the page, we are asked for the median score. Now the median is when put in data, and that's the beauty of the stem-and-leaf diagram. You have all your data in order. When the data is in order, what is the middle value? And just to recap how you do the median, first of all you need to find out where it is. It's halfway along the data set. There's a little formula that allows you to work it out. So you take the number of values you have in the data set. So in this case it happens to be 15. You add 1 and you divide by 2. So in this case 16 divided by 2 is 8. So I'm looking for the 8th value in the data set. So 1, 2, 3, 4, 5, 6, 7, 8. So 103 is the middle value. And for test 2, 1, 2, 3, 4, 5, 6, 7, 8. 106 is the middle value. So we have our two values for the median for each of the tests, and we can see just very quickly what the median is just one of the averages you can work out, and it just gives you a way of being able to sort of get a sense of its central tendency. So in this instance, it seems that the students did better in test 2 because there's a higher median value than in test 1, but only by marginally, but only by three sort of points. Was it greater, not a significant amount. Moving on to part 4, we're asked to work out the mean average value. Now, the mean is the sum of the values divided by the number of values. And in this instance, if you add up 79, 86, 89, 94, etc., etc., all the way up to 111, if you add all those up, you get 1506, and there are 15 values in total, and when you do the division on your calculator, you get 104. The same process with test 2, and you add up all those values from 83 up to 120, you get 1572, and again there's 15 values, and that gives us a mean average of 104.8. And so again we can see that test 2 gives a slightly better result than test 1 by 4.5 points. So test 2 does seem at this stage to be getting higher values than test 1. So moving along to the last two parts, this is where we have the analysis. I've summarised what we had from those previous questions at the top here, and so now we just need to look at it and compare it more formally and just give reasoned argument for what we've actually already discussed. So let's remind us what this is. We had a test, that all the students did the test, and then a week later they did the second test, the same number of students, and we're asked to compare one set of tests against the other. So, how did they do the week later compared to the first week? Now, when it asks for central tendency is a general description. A measure of central tendency is a description of averages, any averages. So we've got mean, the mode, and the median are averages, and a measure of variability. That would be examples of range, interquartile range, and standard deviation. They would be the various different types of measures of spread, I suppose is the best way of describing it. You're talking about the distribution. And so here, if we talk about, for example, the median, we have a situation where test 2 value is greater than test 1, and likewise for the mean, we have also test 2 is greater than test 1. So it's fair to state that the students did better at test 2 than test 1. And for the range, we have a situation where the test 2 range is less than the test 1 range, which gives us a suggestion that there was sort of a less spread out performance. There's more predictable performance, less variability. It would be standard that in any experiment, if you increase the number of trials, in this case number of tests, you'd expect the variations in the results would become less as you do more tests. And this is just shown here as well. It's not a significant difference, it's just a small difference, but they've improved their reliability and their performance. And moving on to the last part, the statement we're asked to discuss is that every student in the class must have done better in test 1 compared to test 2. And the key word there is must. Now, I'm going to say very quickly that the statement cannot definitely be true. So he's not correct. He's not necessarily wrong, but the statement as such is not correct because of the word must. Whilst generally speaking, their performance has improved from test 1 to test 2, and they've become more reliable in their testing, we cannot guarantee for certain that every single student has definitely improved. You could have almost everyone improving, yes, granted, but not necessarily everyone, not every student. And so I've stated that most students will have improved their scores. That's a given. One test, and if you do a test a second time, you know what to expect, and you're more comfortable with the test and the language and so forth. So it would be assumed that they would probably improve their scores, and certainly the data suggests that. But however, 1 or 2 students may have scored less the second time round. Even though that may be unlikely, it is still possible. Therefore, we cannot say that Marshall is definitely correct for all and every student.